All right. Ooh, extra loud today. That should hopefully be better. All right. Welcome, everyone. Hope you had a great weekend. About half of the exams or so are currently graded. Again, we're hoping that the TAs and everyone will have the grades in by tonight. Fingers crossed. But with those about half of the exams being graded or so, the average is right around 77%, which is a great exam one average. So overall, very good. I hope you got a score near the average or above. And so, yeah, I guess we'll have the actual averages and be able to look at a little bit more of the statistics once all of the grades are in. So probably wait maybe until Wednesday. I can maybe talk more about this. But in Thursday's recitation, right, you'll have an opportunity to go over some of the most difficult problems on the exam, or some of the problems that were, students scored lowest on. And so that's going to be part of the recitation on Thursday, right? So there's no review sheet or weekly review sheet on Thursday, but there is an opportunity to kind of reflect back, because of course math builds on itself, right? And you want to make sure that if you saw the same questions again on the final exam, or especially, as we continue to build on it, that you have a good solid foundation. So again, I would highly recommend coming to recitation on Thursday. Yeah, question. 77% is the overall average right now, but this is of course going to change, right? Because only about half the grades are in. So good. Any other questions? Okay. So then today we are continuing the saga of partial derivatives. So last time we spent the majority of our class time talking about kind of the algebra and whatnot, because I know that we're going to get lots of opportunities to practice partial derivatives in 14.4 and 14.5 and 14.6, right? There's going to be tons of partial derivatives kind of from here on out. In this class, we're going to go ahead and apply partial derivatives to an old Calculus 1 game, right? And the Calculus 1 game that we're doing here is back in Calculus 1, you had probably tangent lines, right? And there are lots of great things that tangent lines did, but one of them was approximations, right? So you can use a tangent line to approximate a function's value nearby some set point, right? So I guess this would be at some point I sketch this. So we have some interesting f of x, again, back in Calculus 1, everything was just in 2D. And then you have some tangent line at a given point. And one thing that you can do with the tangent line is to approximate. So these two pink dots here, of course, they're different. They're at different heights, so they're outputting different values, but they are relatively close by. And the closer you are to this point here, right? So if I do maybe a few more dots in purple or something like this, now they're like right on top of one another. And so again, you can use tangent lines to approximate. So we'd like to play the same sort of game, but now in 3 dimensions. And therefore, we're going to have tangent planes rather than tangent lines. So in the pre-class video, we defined a tangent plane. And basically, the thing here is we have some interesting coefficients. This is an equation of a plane still, right? So it should look like the good old equation from a plane from 12.5. But now the coefficients are very specific things. So that way our normal vector is set up in such a way that we're actually tangent to the surface. And so in order to make this happen, we need the coefficient in front of the x stuff to be our x derivative. We need the coefficient in front of the y stuff to be our y derivative. And it doesn't really make sense yet to take z derivatives so much. We will get to this maybe in 14.6. We'll have kind of an upgrade of implicit differentiation. So when we have some general equations, not necessarily functions, of z in terms of x and y, we can still take derivatives and find tangent planes and all that sort of stuff. So I talk a little bit about the proof here of why this works out. And then maybe most interestingly, right, we see some example. So we see an example of how do I create a tangent plane? And again, it relies on these derivatives. So we need to take derivatives of our function with respect to x and with respect to y, find those coefficients and plug them in. And then the last thing that I did was a bit of a definition here. It says that this tangent plane is the linearization. Just like back in Calculus 1, that tangent line was the linearization. So that's the linearization, and we can use that to approximate, again, the function's value nearby some set point. So that is the pre-class video in a nutshell. Any questions about this before we jump into the new stuff for today? All right. So then why don't we go ahead over here. Now that we have that definition for what the linear approximation is, I would like to go ahead and use that. We'll calculate it out, first of all, right? Find the linear approximation for this function at 0, 0. And then, again, I want to use that to approximate the function's value at 0.1, comma, negative 0.2. So, okay. Well, I guess the first thing that I need, let's go ahead and set up my equation. And we can do this either via the tangent plane, or we can use the linearization equation, right? Again, they're the same thing, it's just rearranged. So if I use the linearization equation, let me use blue here, that we had in our box, it was something like this: f of AB plus our x derivative at AB times x minus our x special point, or x special value. And then our y derivative at that special point times y minus our y special value. So when we're trying to find the linear approximation, notice that we're interested in the linearization, and we could ask for it really at any point in space. But here we're interested at a very specific, right, at 0, 0. So this is telling me my a and my b values here, right? So these are the x and the y's that I'm going to be plugging in here. So I could go ahead and start off by evaluating and plugging those in. Let's see, f of 0, 0. Well, I guess I could actually just plug that in and see what my function gives me at 0, 0. So when I plug in 0 for x and 0 for y, it looks like what this goes away and this goes away, and I just get 3 divided by 1. So if I'd like to maybe not take as many steps, 3 divided by 1 is just going to be 3. So at 0, 0, my function's value, the height there, is 3. I'm going to need to spend a little bit of time, and this is where my calculus comes in. And I'm going to need to take a derivative with respect to x and plug in 0, 0. Then I'm also going to need to take a derivative with respect to y and plug in 0, 0. And then those are going to be my coefficients that, again, kind of go in front of my x and my y values, respectively. All right. So now we're on to the calculus bit. So I need to take the derivative of my function with respect to x, and I need to take it with respect to y. So when I personally look at this and think about taking the derivative with respect to x, I tell myself that really the quotient rule here is not needed. Even though we do have a quotient setup here, remember, with respect to x, y is constant. So I'm imagining that y is something like 3 or 5 or just some number. So, right, we have 2x plus 3 and it's divided by some number. All of this to say, kind of, we can rearrange this. And maybe instead of dividing by that 4y plus 1, that's the same thing as multiplying by the reciprocal. So I could write it like this if you'd like. And again, that 1 over 4y plus 1 is just some constant. It might as well be like, what, 1/29th or something like that, or 1/21st, right? It's some constant. So it's along for the ride. So when I take the derivative of this, that constant is, again, just along for the ride with respect to x. And if I'm taking the derivative with respect to x here, well, I'm going to have 2 plus 0, I guess, right? Because the derivative of 2x with respect to x is 2, and the derivative of 3 with respect to x is 0. So we can get 2 divided by 4y plus 1, and that's kind of the fastest way that you could take this partial derivative. Now, if you would like to use the quotient rule, there's nothing wrong with that. Likewise, if I wanted to use the quotient rule to take the derivative of x divided by 5 back in calculus 1, it works out, right? Because the derivative of 5 is 0, and it will give you the correct answer. It'll take you an extra step or so. It's easier to recognize that this is just 1/5 times x, and so the answer will be 1/5. But if you wanted to use the quotient rule, you absolutely can and still get the correct answer. Again, it's just kind of a times situation. All right. So now I can go ahead and take this, and I can plug in 0, 0. So everywhere I see an x, I'm going to plug in a 0. Everywhere I see a y, I'm going to plug in a 0. Again, my problem has me interested in the derivative of f with respect to x at the point 0, 0. So if I plug in 0 everywhere I see an x, 0 everywhere I see a y, well, I don't see any x's, but I do see a y. So this is going to be 2 divided by 0 plus 1, 1. So overall, this coefficient here is going to be a 2. Now we can play the same sort of game when I take the derivative with respect to y, right? So again, if I go ahead and rearrange this 2x plus 3 is now constant with respect to y, right? There are no y's there. There are some x's, but again, we treat x as some constant with respect to y. So this might as well be something, I don't know, like 7, right? It's just some constant. And so when I take the derivative of it, it's just along for the ride. This 2x plus 3 is just some constant along for the ride. And then remember, when we have division, that's the same thing as being raised to the negative first power, right? So really, there's a power rule going on here. When I take the derivative of this, the power rule says, bring down my power, then reduce it by 1. So instead of being raised to the negative first power, it's going to be raised to the negative second power. Leave the inside alone for the time being. Then multiply by the derivative of the inside. And again, the derivative, when I say here, is with respect to y, right? Always with respect to y in this case. Again, if you want to use the quotient rule, you absolutely can, right? And you can get the right answer that way. It'll just end up taking you another step or so. So let's go ahead and try to simplify this a little bit. So let's see, I see a 4, I see a -1, and I see this 2x plus 3, all raised to the first power, right? There's no exponent next to these things. So I'm going to write this as -4 times 2x plus 3. And then this piece right here is raised to the negative second power. Basically, anytime I'm not doing active calculus, right? I'm not taking derivatives or integrals or things like this. I really don't like negative exponents. They're a little bit confusing for me. So I would much rather write this as 4y plus 1 raised to the second power, but in the denominator, right? Use up that negative exponent and push it back down into the denominator using my rules of algebra here. And now again, just like before, my linearization has me interested in this y derivative at a specific point. So when x is equal to 0 and y is equal to 0. So if I go ahead and I plug these things in, let's see, I get -4 times 3 divided by 1 squared. So this ends up being -12. So now I have here both my pieces. Again, I needed a derivative of x at 0, 0 and a derivative with respect to y at 0, 0. So now my linearization equation is going to be 3 plus 2 times x minus 12 times y. And again, this is supposed to be a plane, right? The linearization is just a rearranging of the tangent plane equation. And so we should have, right, x to the first power, y to the first power, right? If you tell me that the linearization of the tangent plane has like x squared, right, I'm going to be confused by that, right? It shouldn't have any x squareds or cube roots of y's or anything like that, right? It should be a nice plane equation. Then the last bit here is that we're going to use this to approximate the function's value. And just like in calculus 1, if you're nearby this point, right, in this case, my 0.1 comma negative 0.2 is pretty close to 0, 0, right? So long as you're pretty close there, you can use this to approximate. So f of 0.1 comma negative 0.2 is going to be approximately equal to the linearization at this point, 0.1 comma negative 0.2. And that we can solve for very quickly by just plugging this in. So we're going to have 3 plus, okay, 2 times 0.1, that's going to be 0.2. And then -12 times negative 0.2, so that's going to be plus 2.4. So altogether, we're going to have, what, 5.6. So the linearization is saying that the height is approximately equal to 5.6. Now, I know, of course, in the age of calculators, right, it's kind of just tempting. If you want to get the exact value, right, you could certainly plug that into your calculator. And hopefully it's somewhat close to this 5.6, and that would be a reassuring way to test, you know, for quizzes and exams and all that sort of stuff. But of course, you have to be careful with the language here, right? We're in a calculus class, and we want to test your calculus skills and all that sort of stuff. And so, you know, using the linearization to approximate this is a good calculus skill. If you just plug it into your calculator, right, you haven't really showcased any of your calculus knowledge. So do be careful on quizzes and exams and whatnot. you know, for linearizations and whatnot to really showcase the method taught in class. All right, that's the end of this one here. Any questions? All right. Well, on kind of the flip side, quite often in Calculus 1, you can either talk about linearization to approximate the function's height, or you can also talk about how much does the function change. And so this bit here is talking about how much maybe the function changes. And so to do that, just like in Calculus 1, we're going to define differentials. So, okay, if we have a couple of small changes of x and of y, so dx and dy, think of these as small change in x and a small change in y. Then the differential, dz, also called the total differential, is given by, and we have dz is equal to, let's see, f sub x at xy times dx plus f sub y at xy times dy. And I wanted to mention, right, that this is not a different idea than linearization. This is really the same idea as linearization. So let me show you here. These line up very nicely. So dz, again, think about this as a small change in your z value. So if it was at z naught, right, and now it's someplace else, right, that's going to be your small change in z. And here you have your partial derivative with respect to x times a small change in x. So again, imagine x is close to x naught, and this is just a small change. That's your dx. And likewise, your derivative with respect to y at some point times a small change in y. So differentials are really the exact same idea as linearization, but it's you're interested in not how tall the function is, right? What is the actual z value? You're interested in how much did the z value change? So with that small change, right, you talk about differentials rather than linearization. And so again, instead of saying that the linear approximation is good at approximating the height's value, we can say that the total differential is good at approximating the amount of change in z. So this delta z is the true change, and this differential is a good way of approximating that. All right. This is certainly worthy of a couple of examples, though, right, to kind of get our head around a little bit better. Question, though. Uh-huh. So the question was, if you put this into the Leibniz notation, then you would see kind of like these dx's and dy's sort of cancel, right? And again, the Leibniz notation is an excellent notation, but they are not literally fractions, right? And so you're seeing this right here, that when you have this two variable case, right, you would end up having two of these, right? Because you kind of, if you allowed the dx's to cancel, right, you would have an f here and an f here, and you would add those together and you have two of them, right? And that would be a bit strange. There's also kind of is a good segue. What the next section is the chain rule. And you see that we will have to kind of take all possible iterations of our partial derivatives. So again, the Leibniz notation is just a notation, so you can't really actually cancel these things. Good way to think of it, though. In the one-dimensional case, it works out very nicely, but not so much in the higher cases, higher dimensional cases. Good. Well, why don't we go ahead and see an example here? So here is a function, and I would like to first calculate out my differential, and then we're going to evaluate it. So according to my formula, dz, I need to take my partial derivative of this with respect to x. So again, this is z is a function of x's and y's. So this right here is my f of xy. So I take the partial derivative first with respect to x. I'm going to get 2x plus 3y minus 0. So again, I'm treating y as constant. It's just along for the ride. So the derivative of x squared, 2x, that one's pretty straightforward. But here the 3 and the y are both constant. They're along for the ride, and so the derivative of x is just 1. And so that's why you get the 3y here. And then the derivative of y squared, that might as well be 3 squared. That might as well be a 9, right? So the derivative of any constant is 0. All right, this right here is going next to my dx. Then I need a partial derivative with respect to y. So I'm going to have 3x minus 2y times dy. So this right here is my differential. Again, we're treating this dx and dy as independent variables in this case. But we're going to get some things to plug in for those, right? So if x changes from 2 to 2.05 and y changes from 3 to 2.96, I'd like to compare the values of delta z and dz. So let's go ahead and first calculate out dz in this case. So dz is going to be equal to, and you always choose the starting values here are always the x's and the y's. So I'm plugging in not the complicated 2.05, but I'm just plugging in 2 everywhere I see an x and 3 everywhere I see a y. So this is going to be what? 4 plus 9 times dx, get to that here in just a second, plus what? 6 minus 6 dy. And again, because I really don't need the dy here just because that's going to be 0. Okay, we'll still calculate it out. Good habit to be in. So if I want to know how much change there is in x, right, my delta x or my dx, either one, right, this is going to be 2.05 minus 2. So it seems like it's changed by 0.05 in the positive direction, right? It's gone up. So my dx here is going to be 0.05. For my dy, or my delta y, we're going to have 2.96 minus 3. So that's going to be negative 0.04. So it's changed by 0.04 in the negative direction, right? It's gone down. It was at 3, but now it's at 2.96. So if I calculate this out, right, it's going to be 13 times 0.05. And that's going to be, you can use a calculator here and get 0.65. So this is an approximation for how much the function's height has changed if you go from the point 2.3 and you change to the point 2.05, 2.96. So the claim is that it's gone up by a little bit more than a half. But again, I would like to compare this one time at least with my value of delta z. So let's go ahead and actually see what this is. So if I was to plug in 2, 3 into my function, let's see, 2 squared is going to be 4 plus 3 times x times y, so 3 times 6, I suppose, and then minus y squared, that's going to be 9. So let's see, I have 4 plus 18 is 22, minus 9 is going to be 13. Now let's see if I was to plug in 2.05, comma 2.96, and this one we really need a calculator for. So I'm going to take my x value and square it. I'm going to add on 3 times x times y. And then I'm going to subtract away what y squared, 2.96 squared. See if I copy that all down correctly. That looks good. So I did this earlier in my office with my calculator, and I got 13.6449. Hopefully, maybe someone else can verify for me that you get this as well. Anyone able to confirm? Which one? 2.05. Oh, so it says I should take x and square it. Yep, so I'm plugging those things in. That's also why there's a 4 here. All right, well, assuming that I did type this in correctly, right? We need to find our change in z. So again, we were at 13, and after moving around, it looks like we're at a height now of 13.6449. And so if you ask for what is the true change in your height, and you subtract these things away, right, you'd get 0.6449. So again, dz is an approximation of how much the function changed, right? It's much easier to calculate this, right, especially by hand, to get the 0.65 versus this 0.6449. So again, that's how much the function has changed. Comparison, if you were asking like the linearization, right? Well, you are at a height of 13.6449. But if you ask how much did you change, right, that's the 0.6449. Any questions on this one here? All right. Well then, like I mentioned here at the bottom, dz is approximately equal to our true change in z, but much easier to compute. Let's do a more applied style problem here. So I have the dimensions of a box, right, are measured to be 10 centimeters, 5 centimeters, and 8 centimeters. But my ruler is not perfect, or maybe I was just going too fast or whatnot, but let's assume that I was at least good enough so that each measurement is correct within 0.2 centimeters. All right, so 1/5. So I'd like to approximate the largest possible error in the volume, right, when the volume of the box is calculated from these measurements. So again, I think that the volume is probably 10 times 5 times 8, right? So that would be 400 cubic centimeters. That's if all of my measurements were perfectly on. However, right, this could be off by a bit. Each measurement can be off by as much as 0.2 centimeters. And so I'm looking for, again, this kind of largest possible error. So how much could we be off by? And so this is going to be an application, right? Error is going to be what is the difference between what I think the volume is versus what the maximum it actually could be, right? So I want to know this error, this difference in my volumes. So because I'm interested in a difference, right, I'm interested in really differentials. Differentials would be a great way to approximate this. So ultimately, I am interested in dV. So I'd like to calculate out my differential of the volume of the box here. So maybe it would first help to remind us the volume equation for these things, right? So for a box, volume is typically the length times the width times the height. I'm going to use x times y times z, just because those are typical variables that we like to use. And so already you can see that I'm upgrading on us, right? I don't just have x's and y's, but now you can see that this volume equation here actually relies on 3 variables. So I'm going to be doing a differential with actually 3 independent variables here. So in this case, right, z doesn't really, this 8 centimeters doesn't really rely on the 10 or the 5, right? They could all be different. So there are 3 independent variables here. And so, well, the differentials, according to, the formula on the last page, are supposed to be something like the derivative of my function with respect to x times dx, the derivative of my function with respect to y times dy. But now I have this third variable introduced, right? I have this height, this z value. So likewise, I'm going to need to take the volume with respect to z, or my derivative with respect to z, times how much the z's could change. Now, when it's talking about this, each measurement is correct within 0.2 centimeters or 1/5 of a centimeter, right? This is saying, well, each dimension, right? Each measurement here. So this is saying that dx is going to be equal to 1/5, dy is going to be equal to 1/5, and dz is going to be equal to 1/5. Right? Each measurement is correct. This is my small change, how much my x's could be off, how much my y's could be off, how much my z's could be off. And again, all these technically have units of centimeters. So I'm going to be plugging these things in, right? There's going to be 1/5, and 1/5, 1/5. But I also need to take my derivatives. So, right, if I go back here and I take the derivative of this with respect to x, and again, now my y's and z's are constant with respect to x, right? They're all independent variables. And so when I take the derivative of this, I'm going to get what, 1 for when my derivative of x, and then I'm going to have a y, z along for the ride. Those are just constants. Likewise, when I take the derivative with respect to y, right? I'm going to have my x and my z are along for the ride, and the derivative of y is just 1. And then finally, when I take my derivative with respect to z, again, my x's and y's are now constant. They're along for the ride. So we get my derivative of z is 1. So lastly, if I want to actually get a number out, right, for this, how much could my volume be off? What is my dV, my change in my volume, right? Well, I need to plug in things for x and for y and for z. So luckily, I have some measurements up here. Let's say this one's x, this one's y, and this one's z. If you rearrange these, by the way, if you want like your x to be 5 centimeters and your z to be 10 centimeters, right, that's also fine. We'll all get the same answer. We'll have a slightly different intermediate step, but we'll all get the same result. So, okay, x is 10, y is 5, z is 8. So here we have 5 times 8. Here we have, what, 10 times 8. And here we have, what, my 10 times 5. So there's a bit of cancellation that can happen here. And I'm going to have 8 plus 16 plus 10. So we're going to have, what, 24, 34. And if you follow the units, of course, right, this is a change in volume. So my units are going to be cubic centimeters. So again, I'm pretty sure that I can hold 400 cubic centimeters in this box. But I was measuring fast and whatnot, so this could be off by as much as 34 cubic centimeters, right? Maybe I have that in the positive direction, maybe I have it in the negative direction. Again, it doesn't say if these were smaller measurements or larger measurements, right? So that's the 34 centimeters, and it could be plus or minus. All right. Any questions on this one here? Okay, well, let me go ahead and formalize this then a bit and just mention that not only can you do this bit with differentials, upgrade it to 3D case, right? You can also do the same thing with linear approximation. You would get some, it's technically called a hyperplane. So line, plane, hyperplane. It's kind of the order of these things. So here, if you have some function that relies on x's, y's, and z's, again, it looks pretty similar, except for you sprinkle in some z's. And likewise, oh, apparently I have an extra plus sign here. You can do the same sort of deal with your differential and just sprinkle in that last term, right? So if you have 4 variables, again, you just add in that, one more term here. All right. So my last page, my last problem here for us is showcasing that although what we've learned here, is good, and we'll use this to get some tangent plane and whatnot, and answer some questions here about when it's horizontal. We will be redoing this problem come 14.6. That when you have a implicit equation like this that kind of gives you a surface, but it's not a function, right? We'll see that this is a little bit painful to apply this tangent plane equation as is. So we will eventually be getting an upgrade for this, but for the time being, this is excellent practice for us being able to solve and find tangent planes, because this is a bit of a harder example. Sorry, yes, question.
Aren't they the same? Even if you have like a surface equation, you put in an x and a y, you're going to get right?
Yeah, so the question was, what is the difference between a surface and a function? So if you have a function, and I guess we need to be specific about the number of variables and stuff like this. So if you have a function, f of x, y, and that those outputs you were to map to various heights, right? And not like temperatures or things like this, but if you were to graph them visually, right? This would give you a surface. So some interesting, right, surface in space, right? Now, on the flip side of that, right, you may have surfaces that are not functions. So for instance, the easiest one that we have is back from 12.1, the sphere, right? So just like in our algebra days, right, functions, there must be one output for every input, right? So if you give me an XY coordinate pair, there needs to be one Z output for each input. But if you give me an XY coordinate pair, you could be talking about up here on the top half of the sphere or down here on the bottom half of the sphere, right? There's not one output for that input, right? That point, that XY pair, that input that you're giving me. And so that's why there are surfaces, right, that are not functions, that do not have one output. They could have 2 or 5 or whatever, right? They could have many outputs actually. So that's the difference between surfaces versus functions. Functions will always have one output, and there's something like a vertical line test, right, that they pass. Good. So this one here, I would like to find the equation of the tangent plane to this surface at the point, right? So this is not a function as it stands. And our tangent line equation, everything, it always requires us to have a z equals some function of x's and y's. So really, I need a z equals. So first of all, I notice that this is not set up as a z equals. So I need to spend a little bit of time rearranging this. So let's rearrange it a bit. So z squared over 9 is equal to 1 minus x squared minus y squared over 9. Let's multiply through by 9 now. Again, I'm trying to get a z equals here. And then finally, I'd want to take the square root. Now, when I take the square root, I need the plus and the minus in order to get the full surface here. We know this equation here, I mean, it kind of even looks like our equation of a sphere. If those 9s weren't there, this would be an equation of a sphere. Those 9s are just stretching this out a little bit in the y and the z direction, right? So it turns out this thing here is actually an ellipsoid. So this is an ellipsoid here. So I'll draw, I don't know. I don't think it's stretched out like quite like this, but still I'll draw it just kind of visualize here. And I would still, though, like to find the tangent plane equation because, right, for my tangent plane, I have it at a very specific point. I want my tangent plane at the point 1/3, 2, 2. And in particular here, I notice that the z value, the output, is positive, right? It's a positive 2. If it was a negative 2, right, that would be on the bottom half. Because it's a positive 2, it's on the top half, right? And so if I would like to get the tangent plane equation when a z value is 2, that means I'm going to be choosing the top half of my ellipse. And now I have a z equals equation that I can find tangent planes for, at least on the top half of the ellipse. This won't help me so much on the bottom half, but luckily this doesn't care so much about that. It's only interested in the top half for now. So I have my z equals equation. And with that, I can find, right, my equation for a tangent plane. So my tangent plane equation, remember, goes like this. Z minus some z special value is equal to the partial derivative with respect to x at my special values of x and y times x minus x naught plus the partial derivative with respect to y at the special point times y minus my y special value here, y naught. So again, we are interested in our special value here is 1/3, 2, 2. So our x special value is 1/3, x naught is 1/3. I'm putting at 2 for y naught, and for z naught, right, also at 2. So now I can plug in a decent amount of this. 1/3, 2 times x minus 1/3. 1/3 comma 2 times y minus 2. So now I'm just plugging in everywhere I see my x naught, y naught, z naught with my specific values, 1/3, 2, 2. And now we really get to the meat of this, right? Because I need to perform some calculus in order to find these partial derivatives. So again, here is my function equation, and this is what I need to take the derivative with respect to, or derivative of with respect to x and y. So let's go ahead and take the derivative with respect to x. The outermost thing here is that there's a square root. Remember, the square root is the same thing as the 1/2 power. So the 1/2 is going to come down, and I'm going to reduce my power by 1 according to the power rule. We leave the inside alone. Then we multiply by the derivative of the inside. So the derivative of 9 with respect to x, well, it's constant, so we get 0. The derivative of negative 9x squared is going to be negative 18x. And the derivative of negative y squared, again, with respect to x, that's just constant. It might as well be like a 3 squared or a 9, right? Something like this. It's just 0 then when we take the derivative of it. So the derivative of the inside is just negative 18x. We can simplify this a little bit, right? The 18 and the 1/2 will cancel out a bit, and we'll get 9. And so we'll have negative 9x in my numerator. And in my denominator, I'm going to write this as the square root of 9 minus my 9x squared minus my y squared. So again, I'm using up that negative 1/2 power I saw there. The negative piece means that it's really in the denominator. And then the 1/2 means that there's a square root. Now I'd like to go ahead and evaluate this at 1/3, 2. So let's see, negative 9 times my x is 1/3, so that's going to be negative 3 in the top here, divided by, and we have the square root of 9 minus 9, and we have 1/3 squared, that's going to be 1/9, minus 2 squared. So we have 9 minus 1 minus 4. So it's going to be minus 5 altogether. So 9 minus 5 is going to be 4. So this is the square root of 4, which happens to be nice, even 2. Maybe I won't spend as much time on this one. The story is very, very similar here. We need to have the 1/2 come down, leave the inside alone, reduce our power by 1. And then when we multiply by the derivative of the inside, we're not going to get negative 18x in this case. What are we going to get when we take my derivative with respect to y? Negative 2y, right? Good. So again, there can be a little bit of cancellation. We're going to have negative y divided by this square root of stuff. And then when I go and I plug this in, right, f sub y at 1/3, 2. In my numerator here, I'm going to have negative 2. And in my denominator, I already did all the work, right? I know we're plugging in the same numbers, and the denominator is the exact same here. We're going to get this 2 on the bottom again. So after that, all simplifies down, we get a negative 1. So my final answer, z minus 2, is equal to negative 3/2 x minus 1/3 minus 1 times my y minus 2. And that right there is my tangent plane equation. back in 12.5, we like to have maybe all of the variables on the same side. If you'd like to, you can rearrange that and get all of the variables on the same side. But this is the first place where we have the full tangent plane equation. All right. I want to at least talk through the idea because it's conceptually interesting, these questions. Find the points at which the tangent plane to the surface is horizontal. And when is the tangent plane vertical? So if I was to go back and think about my tangent plane, and I know that, again, my surface is an ellipse, so something like this. And again, it may be stretched out a little bit differently. And I think about, where is my tangent plane completely horizontal, right? So at this point, I found the tangent plane equation maybe off to the side here. It's a little bit cockeyed like this, but okay. That was my tangent plane, maybe originally. Can anyone tell me where is a place going to be where the tangent plane is completely horizontal? Just graphically, not maybe with the equations, but yeah. The top and the bottom, right? So we'd expect up here at the very top that this is going to be one place where kind of tangent to this, right? You can just barely skim the surface here. And you can do that horizontally, and that should be one place. And then also at the bottom. Graphically, so we have a good understanding of what this means. What this means when we talk about partial derivatives, well, this means that we would like the amount is, if we step in the x direction, not to go up and down at all. So that means that if I don't want to go up and down at all, my x derivative, which should be 0. And if I take a step in the y direction, I shouldn't go up and down at all, right? Again, it should be no change whatsoever. So my y derivative ought to be 0. So you want both of these things to be true if you want a horizontal tangent plane. So if I go back to my equations here, and I take f sub x, which again was equal to negative 9x divided by the square root of stuff. And I ask you, how can I make this 0? Well, it's a fraction. You could cross multiply here, and you would get negative 9x should be equal to 0. And therefore, the only place that it happens is at x equals 0. So that's only, right, using I want my f sub x to be equal to 0. If you want your f sub y to be equal to 0, you can do very similar steps. And in this case, you can find out that that happens exactly when y is equal to 0. So if you want both of these things to be true, you want your f sub x, your x partial derivative to be 0, and your f sub y, your y partial derivative to be 0, you need x to be 0 and y to be equal to 0. So that means you're at the point 0, 0. Now this was all done for the top half of the ellipse, or the top half of the ellipsoid, right? You need to do something very similar, right? Or just think about it graphically to get the fact that the bottom half also has a horizontal tangent. So the last bit here is just, we won't do the math exactly, but just thinking about it graphically. Can anyone tell me a place where the tangent plane is going to be vertical, straight up and down? I see the right motion here. Yeah, so along this equator here, if we can call it that, anytime you take a plane and you attach it to the equator, right, it's going to have this straight up and down aspect to it. What this turns out to be mathematically is either f sub x is undefined, or if your f sub y is undefined. So essentially we're dividing by 0. It's kind of like, for a vertical line, the slope of a vertical line is undefined, right? It's like you're dividing by 0 there when you do your rise over run. It's the same sort of deal here. It's essentially your slope, your derivatives, right, are undefined. It's like you're dividing by 0. So the question is, how do you take this right here, and what sort of situation would you need in order to be dividing by 0? Well, you have this thing that's inside of your division and inside of your square root. Figure out when that's equal to 0. And it turns out that that equation is exactly the equator there. So, all right. Well, With that, I will go ahead and post the, final answer for C on D2L here later today. But yeah. Welcome back, everyone, and see you on Wednesday. We'll talk about the chain rule.